tonight. So here we go. Once again, we're talking about a math adventure, Circumference and the Sword in the Cone. Once again, a math adventure, Circumference and the Sword in the Cone. And the caption here is a three-dimensional solid. So that is what we are talking about. Once again, Miss Cindy Neuschwander. This is a great creative idea that she has come up with. And folks, the illustrator Wayne Jihan is awesome with all of the Circumference books. So you may not be able to see the words I'm reading to you, but please, James Brown, please look at all of the artwork that Wayne Jihan is doing for all of us here. So I'm ready to get into this wonderful book right here, talking about a sword in cone. Make sure we're good to go. And here we go. Look at these beautiful pictures right here. One fine morning, Circumference, Lady Diameter, and their son Radius sat eating breakfast in King Arthur's castle. Suddenly, the doors flew open and a young knight ran into the room. It was Vertex, Radius's best friend. Wink, wink. I found out why King Arthur called us all here, Vertex exclaimed. I said wink, wink because guess what? All of the characters have mathematical names, and I think it's awesome. The king wants to choose an heir, Vertex explained. 5 knights are competing for the honor. I'm one of them. You would make a fine king, Circumference said. That's right, agreed Radius. You helped the king make peace with the Euclideans last year. Yes, but now I have to solve the puzzle on this parchment. Parchment is a special type of like wax paper. Vertex said, the king has hidden his sword. Oh, Edge Caliber, not Excalibur, but here they call it Edge Caliber. I love to play on math words. The knight who finds it will be the next king. Ooh, sound like a treasure hunt to me, folks. Vertex unrolled a parchment. This is the only clue the king gave us. Form the solids and find their places. How many edges, points, and faces? The shapes that make 2 will pass the test, but one that does not must be your quest. 3 times as tall as its base is wide. The true king's future lies inside. Interesting. As I stated before, we're talking about edges, points, and of course faces, and all of those are contained where? Within 3D shapes. We're talking about geometry. Look at the strange drawings, Lady Di remarked. They look like wooden tabletops. Let's go ask the carpenters, suggested Radius. They know a lot about building tables. Ooh, look at this. Vertex and Radius ran down to the country yard. They saw the other knights trying to find Edge Caliber. One knight was carving solid shapes out of wood. Another knight was counting the edges of each stone in the castle. A third knight was inspecting the points of several swords. The last knight was looking through school books for tests with the number 2. I know a shortcut, said Radius. He led Vertex into a tunnel. This will take us under the courtyard to the carpenter's workshop. The tunnel was dimly lit, and scratching and squeaking came from the dark shadows. When they got to the workshop, Vertex showed the carpenter's geo and sim of Mitri the drawings of the parchment. "Do you know what these are?" he asked. "Yes," answered Geo. "These are diagrams showing solid shapes flattened out. You can use them to make shapes with height, length, and width," added his brother Sim. "I see," nodded Vertex. "Let's try it, Radius." Okay. In mathematics, we call those shaped nets. We call those nets. So what he realizes on the parchment paper, they are going to be geometric nets, which will create actual 3D or solid shapes. That's going to be interesting. We must find Excalibur. Vertex and Radius cut and folded the shapes. The parchment says, "The shapes that makes two will pass the test," Vertex said. "This cube has 6 square sides or faces, 8 corner points, and 12 edges, where the faces come together. How do you get a 2 from that?" "Look at this pyramid," said Radius. "It has 5 faces, 5 points, and 8 edges. I don't see a 2 anywhere." "Maybe we have to add the number of faces and the number of points," said Vertex. "If we add the pyramid faces and points, we get 10. 10 minus 8 edges is 2. "Does it work for the cube too?" asked Radius. "The cube's 6 faces plus its 8 points is 14. 14 minus the 12 edges is 2. I think you've got it, Vertex." Okay, they making discoveries today. Oh, perfect. As you can see right here, they in the picture they talk about flat faces, corner points, faces and points, straight edges, and then they got faces plus points and edges, and all of them equal 2. And it's interesting. They show the shape of the cube, the shape of the pyramid, the shape of a rectangular prism, and the shape of a triangular prism. Okay. We'll take a look at these in just a few moments after I finish reading. Vertex and Radius finished making the shapes. There were cubes, pyramids, rectangular prisms, triangular prisms, cylinders, and cones. Vertex counted the faces, corner points, and edges of each shape. He added the number of the faces and points, then subtracted the number of edges. The answer was 2 each time, except for the cylinder and the cone. Except for the cylinder and the cone. I wonder why. Vertex unrolled the parchment and read again. "The shapes that make 2 will pass the test, but one that does not must be your quest. The cylinder doesn't have any points, and the cone doesn't have any straight edges. They can't make 2 and pass the test. Our next clue must be a cylinder or a cone," he announced. "Look at this," said Radius. "I made a model of the castle with the shapes. Here is the pyramid roof on top of the rectangular tower. The other towers are the cylinders with their cone-shaped roofs." Vertex looked at the model. "Let's search for Excalibur in the round towers, since they are built in the shape of cones and cylinders. Interesting. Vertex and Radius climbed up and down the spiral staircase in each round tower. They looked under every trapdoor, in every suit of armor, and behind every tapestry, but there was no sign of Excalibur. I wonder where Excalibur could be. Are they following the correct clues? What do you think? Let's search from above, Vertex said. They went up to the roof. Vertex had a commanding view of the castle country yard. Look at the stones in the path, he said. Each of those round paving stones could be the bottom of a cone or cylinder. Why? Because they're circle. That path is the same direction as the tunnel we went through. Okay, interesting. Uh-oh, it looks like it's a lot, though. Vertex and Radius returned to the tunnel. Sharp points jetted down from the ceiling. These points could be the tip of cones, Radius said. We need to dig them up, said Vertex. Vertex and Radius waited until nightfall. When the courtyard was empty, Vertex remembered the words of the parchment. 3 times as tall as its base is wide. The true king's future lies inside. If the base of a cone is its circular bottom, we need to measure the width of these paving stones. Vertex measured one of the stones. This cone is 14 inches across its base, he said. So it must have a height of 42 inches to be 3 times as tall, Radius replied. Okay. So now they're doing a little math right here so they can solve the mystery. Uh-oh, they're starting to dig. Look at the picture right here. They're starting to dig up things. Let's see what's going to happen. Vertex and Radius dug up the cone. It was 47 inches high. Oh, no, said Radius. It's more than 3 times as tall. Let's try another one, suggested Vertex. He and Radius dug all night. They unearthed and measured many cones, but none was right. Some were too tall, and you guessed it, and some were too short. They still had many cones to go when the full moon set and the day began to dawn. We'll never finish, groaned Radius. We've looked for clues in the tunnel and dug up lots of cones. Where else can we look? That's a good question. What do you think? Where else do you think he could look? Where else do you think he could look? We've looked over the cones, under the cones, and on the cones. But what if Excalibur is hidden inside a cone? Oh, good thinking, suggested Vertex. Are any of them big enough? Excalibur is a sword, so it has to be about 48 inches long, about the same length as this shovel. Vertex asked, Radius, will you go back down into the tunnel? Soon Vertex heard Radius's voice from below. I'm in the tunnel, tunnel. But what am I looking for? Interesting, interesting. Oh, he's digging up 4 more cones. Vertex placed the shovel in the nearest hole. Can you see any cones that are long as the shovel? I see 4 cones that are about the same length, Radius answered. Excalibur could be hidden inside any one of those cones, Vertex said. But the cone we seek must be 3 times as tall as the base is wide. 48 inches divided by 3 is 16, said Vertex. He measured the base of the 4 cones. All were more than 16 inches, but the last one was close. As the sun peeped over the horizon, Vertex started to dig. Do you think it's in here? I don't know. We're going to find out in just a second. Because them boys been digging all night long. All night long. Yes. Radius ran back to the courtyard. Vertex heaved and tugged on the stone. Finally, he pulled up a large cone. Vertex measured it. It was exactly 51 inches high, 3 times the 17-inch of its base. Yes, sir. Vertex pried off the base of the cone and pulled out a gleaming sword. Excalibur is found, he exclaimed. Yes! Okay. Woo, so that hard work and that digging paid off. And they use clues. All right, let's see. As Vertex held the sword aloft, everyone in the castle came running out. King Arthur said, "You have solved my puzzle, Sir Vertex. Tell us how you use your wit and will to find Excalibur." Vertex bowed low. "Sire," he said, "I folded each of the diagrams on a parchment into a solid shape. Then for each solid, I added the number of faces to the number of points and subtracted the number of edges. The answer was always 2 until I got to the cylinder and the cone. So Radius and I searched the parts of the castle shaped like cylinders and cones. We found these cones buried in the courtyard. One of them was 3 times as tall as its base was wide. Excalibur was inside." Very good. Vertex knelt and held out the sword. King Arthur smiled. "Sir Vertex, you have used your intelligence to earn the greatest honor that I can bestow." The king took out Excalibur and tapped Vertex on each shoulder. "I.W. Prince Vertex, when I can no longer rule, you shall be my king. Rise now and greet your subjects. In your hand, their future is in solid shape." The crowd cheered. "Hip, hip, hooray! Hip, hip, hooray! Hip, hip, hooray!" Vertex said, "I want to thank Sir Cumference, Lady Di of Amateur, and Radius. They helped me measure up to the challenge. I hope they will be my advisors when I am king." Vertex eventually did become a wise and thoughtful king, known to his people as Vertex, the Lion-Hearted. The Lion-Hearted, get it? To this day, the point at the heart of 2 or more lines is called a vertex. There really is a mathematical twos test for geometric solids. It is called Euler's Law. A Swiss mathematician named Leonard Euler provided in 1751 that if you add the number of faces on a geometric solid to the number of its points, which is the vertices, and then subtract the number of its edges, the answer will always be 2. It works for any it works for any polyhedron, which is a straight-sided solid shape. The key word there was a straight-sided solid shape. Okay? So that's where the problem came in because of the cylinder and the cone, because they don't really have any edges. This was a wonderful book. And once again, this is a series. As you understand, the past 4 weeks, I've been talking about circumference, lady of diameter, and of course radius. And of course, the main character is Circumference. And you're talking about King Arthur and a whole lot of kings and knights. And of course, the name of the story is A Math Adventure, Circumference and the Sword in Cone. And of course, the caption here, this is 3-dimensional solids. And once again, please look up this. I got these online. Cindy Neuschwander, illustrated by Wayne G. Hahn. This is a wonderful series. It's about 10 books in this series, and I hope that you get a chance to take a look at this. What I do want to focus on real quick is actually talking about the edges and faces of some of these 3-dimensional shapes. So let me turn back to this page right here, and we'll talk about a little vocabulary real quick. And as you can see here, we're talking about the cube. And of course, here you have your cube. And what you understand here is an actual cube. This is our cube right here. And here with our cube right here, yes, it has 6 flat faces. One of the key things that I like is in Vegas, because Las Vegas Raiders won last night. I can talk about Vegas real quick. You have this thing in Vegas, they roll the dice, okay? And of course, a die, the highest number on a true die is the number 6. Why is it the highest number of number 6? Because guess what? With our cube, it has 6 faces, okay? And if I hold it like this between my fingers, guess what? I have a top and a bottom, opposites. I have a left and I have a right, okay? And of course, I have a front and a back. So that's how you get your 6 sides. You got a top and a bottom, okay? A left and a right, and a front and a back, okay? So that's how you get your cube right there, and that's how you get your 6 faces. Now, it says it has 8 corners. Let's see, can I do this real quick? It's been a while since I've done this, but I'm going to use my, not get rid of my middle finger, but I used to go 1, 2, 3, 4. Okay, and I'm going to get rid of my middle finger here and go 5, 6, 7, 8. I got rid of my middle fingers, and because I got rid of my middle fingers, I'm able to actually touch all 8. They call them here corners, all corners. So we got, that's correct in the cube. It has 6 flat faces, check. It has 8 corners, okay? 8 corners. Now, the other thing that we have up here is we have the actual edges on here. We have the actual edges. And when we talk about the edges, I don't know if you can see them or not, but the edges are the pieces that make this up right here. These are our edges, okay? 1, 2, 3, 4, 5, 6, 7, 8. Okay, 9, 10, 11, 12. There are a total of 12 edges. And so we put a check mark with that as well too. How many straight edges on a cube? It will be 12, just like it says here in the book. Okay, now they did not do that like I wanted them to, but the cube has the same information of faces, corners, and edges as the rectangular prism. Now, some people say a rectangular prism is it's just like cutting it in half. Okay, and right now these are two representations of rectangular prisms. The key difference is guess what? In a cube, all faces are squares. In a cube, all faces, all flat surfaces are equal. All flat surfaces are squares. And so since it's all squares, okay, it's going to be a cube. On the other hand, you have a rectangular prism. With our rectangular prism, guess what? It's the same dimensions, has the same amount of flat faces, 6. Okay? It also has the same amount of corners, 8. And that's what we got going on right here in our book. 6, 8, okay, and then 12. This right here, this column here, talks about the straight edges. So when we talk about the rectangular prism and we talk about the cube, they are in the same family. Okay, and they are 3D shapes. And the cool part is when you see these right here, if you are a Amazon fan like I am, your boxes come in these different shapes right here. Okay, so that's what we're taking a look at right here. Some are taller than others, because with this one right here, I can set it up. Okay, so right now, everybody say cube. 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 Great job. Put him to the side. All right. These both are the same right here. Everybody say rectangular prism. Great. Everybody say rectangular prism. Great. And this one also is everybody say rectangular prism. Great. Rectangular prism. Great. All right, can put them to the side. The next one they talk about here is what they call a square-based pyramid. A square-based pyramid. When we talk about a square-based pyramid, we are talking about that thing that is located in Egypt. One of the great mysteries of how they built it. A lot of great mathematical geniuses came out of Egypt. A lot of geometric theories came out of Egypt. And one of the key things here is, in this case right here, why is it called a square-based pyramid? Very simple, folks. Guess what? It has the base of a square. It has the base of a square. And since it has the base of a square, that is what they talk about. So it has two shapes that are involved in it. The first shape is a base that's a square. And then the other faces are triangular faces. They have triangular faces, and they all meet at one point. They all meet at one point. So technically, this has 1, 2, 3, 4, 5. As it says right here, it has 5. It has 5 flat faces. It has 4 triangular faces and 1 square base. Okay? And that's why they call it a square base pyramid. And I didn't show it today, but guess what? There's also a triangular base pyramid. But in Egypt and most of the other pyramids that are known have a square base. Next, the corners. The corners, or the sharp points on the pyramid, is going to be 5. 1, 2, 3, 4, 5. Why is it 5? Because you have your square at the bottom. because you have your square at the bottom, guess what? That's 1, 2, 3, 4. And then all of them form one more point, okay, or corner at the very top. So when we talk about the pyramid, you have 5 flat faces. Check. You have 5 corners, okay? Now, the other thing is this, not 12 like the cube or the rectangular prism, but the pyramid has 8. It has 8 edges. It has 8 edges. What do you mean, Mr. Jones, 8 edges? By holding this up right here, the edges is going to go here. 1, 2, 3, 4. There are 4 that are going to be formed by the triangles up here. And then, of course, if you turn back to the base, I keep talking about that base, don't I? It's important. 1, 2, 3, 4. And, of course, 4 plus 4 gives us 8. So when we talk about our square base pyramid, it has 5 flat faces, check. It has 5 corners, check. And it has 8 straight edges, check. All right. Everybody say square base pyramid. Great. One more time, square base pyramid, check. All right. Now, the next one is called a triangular prism. A triangular prism. Would you just say, Mr. Jones, a triangular prism? Yep. Now, when I look at a triangular prism, I am a former member of the Boy Scouts of America, and I spent many summers at Camp T. Brady Saunders in Matins, Virginia. And when I think of this, this triangular prism, what I think about is the tents that I had to sleep in. Our tents were in a triangular face, but it had the base of rectangles. Okay? It had the base of rectangles. So in a triangular prism, it has faces that are made up of rectangles and, of course, triangles as well, too. So a lot of the tents nowadays are dome shaped, like this right here, this semicircle right here, okay? But if you go to the camping, I think they still have those tents right there. They were a real green color. I miss those days. Miss those hot summer days too. But had a whole lot of fun out there with the Boy Scouts. So if you get a chance to see that, also too, there's some roofs that look like this, okay? What are we talking about right now? We're talking about the triangular pyramid. What the gentleman in our story measured in a triangular pyramid, they measured here. They said it has 5 flat faces just like the pyramid. It has 5 flat faces. All right, let's see what we got. Of course, if you already know about a triangle, how many sides does a triangle have? A triangle has 3 sides. So what's happening when you connect the 2 triangular bases, okay? I said 2 triangular bases because 1, 2. So that's 2 of them right there. The other 3 are going to come from the 3 rectangular sides. So that's why we have 5 flat faces. The next one says it has 6 corners. Oh, that's a big difference. The pyramid had 5, but the triangular prism has 6. All right, let's see why. Once again, you have a base that's a rectangle. 1, 2, 3, 4. All right, so we're good with that right there. But this one doesn't meet. Like the square base pyramid, everything comes together at one point. It comes together here at the point. But guess what? With our triangular prism, it comes together at 2 points. It comes together at the 2 points right here. Okay? So that's why for your corners, it has 1, 2, 3, 4, 5, 6. That is awesome. All right, so it has 5 flat faces, check. It has 6 corners, check. All right, but this is weird. This one said it has 9 straight edges. This says this has 9 straight edges. So let me see, can I find those? All right, the easiest one is going to be the square here at the bottom, or the rectangle. So I'm going to go 1, 2, 3, 4. That's my 4 right there. All right, let's see here. That's 4. All right, so I'm done with that. So now I got to go here. 5, 6, 7, 8. 9 is the one that goes across the top. All right, once again, I can't count the bottom one twice, so that's why I said it flat in my hand. But at the bottom here, you have 1, 2, 3, 4. And I put it flat in my hand. Once I put it flat in my hand, then guess what? I can now count 4, 5, 6 for the front, 7, 8 for the back, and then the one at the top, which gives us 9. Wow. So this has 9 straight edges. Wow, this is awesome. Okay? And so that is what he said for the prisms right here. And what he was telling us in here, let me go back to the back and read this again. And it says, there really is a mathematical twos test for geometry solids. It's called the Euler's Law. A Swiss mathematician named Leonard Euler proved it in 1751, that if you add the number of faces, okay, we talked about faces, on a geometric solid to the number of its points, which is your vertices, and then subtract the number of its edges, the answer will always be 2. It works for any polyhedron, straight-sided solid shape. So these are our come on, Jones. Our straight-sided solid shapes. Oh, that's that S tongue twister. Rubber baby bubble bunk. I can't say that one either. All right. Let me say that one more time so I can stay out of trouble. Straight-sided solid shapes. All right. Say that 3 times fast. All right. Now, the thing that he did to become king, that Vertex found to be king, he looked at these shapes right here. He looked at a cylinder and he looked at a cone. He looked at a cylinder, he looked at a cylinder, and he looked at a cone. Okay? Now, some other circular shapes, just to get it out of the way, another 3-dimensional shape right here is my baseball, my basketball, my volleyball. We call that a sphere. Okay? It's a circular. Okay? It has no edges. No edges. It has no edges. Okay? It has no faces. Okay? It doesn't have anything. Okay? So this one's going to go to the side, but it's still considered a 3-dimensional shape, known as a sphere. All right? Hopefully she won't roll away. That's the only thing I don't like about the sphere, because it likes to roll. Okay? But once you slice it in half, guess what? It's still considered to be in the circle family. And we have to use pi and a whole lot of other stuff to find out different mathematical things about the sphere. The other 2 that we talked about were the last 2 shapes that he had. And I'm going to add another one in here. Okay, and I have 2 cylinders. I have like a skinny cylinder and a more of a fat cylinder. Okay, now with my cylinders, both of them have 2 faces that are circular. They have 2 circular faces, both of them here. Okay, now even though they're different sizes, even though they're different colors, okay, that term is similar. Okay, I like that one. They're similar. They're not congruent. To be congruent, it has to be the same size and, of course, the same shape. But in this case right here, they're similar. Okay, why? Because they are similar shapes. And when I look at this right now, I'm thinking of a can of soup. I'm thinking of a can of soda. Okay. And I'm looking at some of the packages that I get my posters in from Amazon. They come in a cylinder type shape, because you have to have a top and a bottom to close. Top and a bottom to close. Now, with our rectangular prism, they had edges. Notice because of the circle, because of the circle, there are no edges. There are no edges. So that's why they kind of knocked them out of the 2 rule. Okay, I'm just able to go around here. Now, are there faces? Yes. There are 2 circular faces. So they got faces, yes. All right. Now, they don't have any corners. They don't have any edges, nor do they have any corners. Why? Because everything is rounded. Okay? Everything is rounded. Okay? Everything is rounded. Okay? These are mine. Everybody say cylinder. Great. Cylinder. Cylinder. And of course, right now, this is a skinnier one. Everybody say cylinder. Look like a big piece of sidewalk chalk. Yeah, it's a big yellow. I'm going to go right on the table. No. All right, so that, but guess what? It's still considered to be a what? 3-dimensional solid shape. And now, ladies and gentlemen, the star of our show this evening. Everybody say hello, Mr. Cone. Okay, this is the star of our show. Once again, guess what? Going around here, there are no edges. There are no edges. Why? Because this has a circular base. Because of the circular base, it has no edges. Guess what? It has one face. It has one face, and happens to be that the place where this one sits on is the actual base. Okay? And believe it or not, just like our pyramid here, where it all comes at one point up here, guess what? This has one point. Okay? Has one point that it comes to at the very top. All right? Now, when I think of a cone, I think of a party hat. Let's party. Happy birthday to you. Hey, happy birthday to you. Yes. Or, ooh, some good NFL games this weekend, folks. And I saw some people with that little horn. Have you ever seen a trumpet? Hey, it has a circular base and it has this. Or that little noise maker. For everybody who celebrated their team win this week. What I'm trying to tell you, folks, is that 3D solids are everywhere, okay? When you tune into this, those that's tuning in tonight, now I want you to pay attention when you go to school tomorrow, when you go to work tomorrow. Look at all the vehicles. All the vehicles are derived from one of the 3D shapes that we talked about tonight. Yep, okay? From some of your tractor trailer trailers, guess what? Some of them are cylinders. Those that carry liquid, some of them, guess what? Especially gas, are a cylinder shape. Some of them are a cylinder shape, yes. Guess what? Of course, you see the back of a Amazon truck, or you see the back of another type of Pepsi-Cola, Mountain Dew truck. Guess what? It's a rectangular prism. So what am I trying to tell you, folks? Shapes are everywhere. If you go look in your house, if you go look at your church steeple, guess what? All of those things are made up of 3D shapes. So I encourage you to make sure that you continue to look for those 3D shapes, because guess what? They are everywhere. Okay? All right, I want to point it out one more thing in the book, and then I'm going to have to close this thing out for tonight. All right. Come back over here. We're back here. All right, now, what you ask your teacher about this tomorrow. I didn't bring them tonight, but the clue that the king gave him on that parchment paper were a bunch of nets. Now, some of you saying nets? You talking about them little flies? No, not them little pesky little nets like that. Oh, you talking about that thing Shaq be dunking on, them nets? No, not even the New Jersey nets. No, I'm sorry. I'm old school. They Brooklyn now, I think. The Brooklyn Nets. But what we're talking about is if you were able to unfold the shape it would take the shape of a real flat thing. And basically you'll see it makes all the different faces of it. And I'm not sure how much of a close-up we can get up in this book right here, but you can see several of the different nets. And what's happening here is if you go around here, this first one right here is a net for a rectangular prism. This one right here is a net for a rectangular prism. Why? Because you have all rectangular prism. Okay, so it's almost like an unfolded box. Same thing here. Here's another net for a rectangular prism. Okay, why? Because you have square faces, okay, and you have 4 rectangle sides. So that's still 6 sides right there. Going back to this rectangular one right here, you still have, let me make sure, 1, 2, 3, 4, 5. You still have 6 sides. Because this one that's unfolded in here is the piece that you don't see when it's sitting on its base. This one here, this is the cone. This one represents our cone. Okay, why? Because it has a circle and it has like a half of a circle here, and that's what's happened. That's the piece that wraps around the circle and then comes out at a point. And of course here, I think this is their representation of the cube. Why? Because in this drawing, he's trying to show that all sides are the same. So that is a representation of our cube. Okay. So this one right here is our rectangular prism. This one here represents another type of rectangular prism. So rectangular prism. Rectangular prism. This next one represents a cone. This one right here represents a cube. Because all of the faces in the net, are square faces. They repeated this one here. This one, once again, is a rectangular prism where all sides are rectangles. They repeated this one again where you have 2 rectangular, you have 2 square bases and you have rectangular faces. They tried to slide this one in on me right here. But right here, this little small one right here, that has a square in the middle and it has 4 triangulars, which means eventually they'll come up and come to at a point up there. That is my pyramid right there. And right here, you have a circle on one edge. I have a circle on one edge. You fold those in like a can and you roll it up. And that'll give us our cylinder. That's our skinny cylinder right there. It's our skinny cylinder right there. Okay? All right. And they repeated this right here. This is our rectangular prism here. It's our rectangular prism over here. That's our rectangular prism right there. All right, what we got here? That is, there it is. This is our triangular base pyramid right there. What they got right there, they have 1, 2, 3. Yes, they have 3 rectangular shapes, and they have 2 triangle bases right there. So it's made up of 2 triangles and a square. And of course, guess what I'm having here again? I'm having to start a show another cone. Having another cone. And got 2 more. That's going to be, why did they do that? That's a larger one. It's another triangular pyramid right there. That one's a little fatter than that one. That's a little skinny one. That's a little fat one right there. And then finally, at the edge right there, you have your 3D shape right there of a rectangular prism. Okay. And lastly, we have about 3 more minutes and I'm going to close this thing out. I want to go over all of the shapes one more time. I want to go over all of the shapes that we talked about one more time. And of course, I have the star of the show. I'm going to show him at the beginning and at the end since he's the star of the show. Everybody says cone. 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 Good job. I'm going to put him to the side since he's the star of our show. The next one right here, I have a red cube. Like a cube of ice. Like a box. Okay? Cube. 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 Okay? The next shape, rectangular prism. Rectangular prism. Rectangular prism. Rectangular prism. I'm going to put him over here. We have another rectangular prism. Even though it's a different size, okay, we're not getting into our volume tonight. Length times width times height. Not getting to that tonight. But that's on a different thing. They have a different volume with that. Maybe we'll get to that. That's a 6th, 7th grade SOL and EOG. But we'll get to that later on. That's why they're still considered to be rectangular prisms, but they are different sizes because they have a different volume. Don't forget the pyramids. And as you can see, it looks the same no matter how you turn it. It still looks the same. This is our pyramid, but specifically because it has a square as a base, it's known as a square-based pyramid. Next one here is our cylinder. This is our cylinder. Okay, I can flip it here and flip it there. As I said before, it looks like a big old piece of chalk. Okay, and that's a cylinder right there. Cylinder. 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 Okay, and right here, I went back to my old camping days at Camp T. Brady Saunders. Check this out. Shout out to all my former staff members and all the Boy Scouts in America right now. This is an old tent right here, but what do we call this shape? We call this a triangular prism. Okay, called triangular prism. It looks different on the side. Okay, that's the side right there. I turn it. You see the triangles in that side, so it's a big difference. And once again, this is our triangular prism. All right, I have another cylinder here. This one's blue. And of course, this also has a different volume. And of course, when we try to find any information on this, we have to use pi. Because when we talk about the circumference, that's the distance around, we have to use that. But that's for another day. And I put him in the pocket because he likes to roll away. And the last one that has 0 edges, 0 corners, 0 faces is the sphere. Rounded, the ball, the basketball, the baseball. Okay? Everybody says sphere. 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 And, oh, wow. I need to show this to my students tomorrow. This is a half of a circle or a hemisphere. Because we talked about that in Virginia is in the, it should be in the northern hemisphere. Because we are on the continent of North America. Folks, that is my time again today. I want to put the spear right there, and I want to put the cone back out here today. Because guess what we did today, folks? We read our story today about the sword and cone. We read about the sword and cone today, and this was the star of our show today, Mr. Cone himself. So thank you for joining us